Good afternoon. I've been asked very kindly to talk about M31, and namely the X-ray observations of M31. However, Greg was so kind to allow me to also include other galaxies. I'm very generous for it. Thank you very much. So, X-ray observations, X-ray observations of M31 and other nearby, I would say, low-mass elliptical galaxies. As Brent briefly mentioned, the bulge of M31 is a very old population, so we can almost consider it as an elliptical galaxy, right? And since it has like a few times 10 to the 10 solar masses, so we consider it as a low-mass elliptical galaxy now in this presentation. So, this is the first slide. Let me just summarize the result. So, the result is, as Brent also already mentioned, is that in the bulge of M31 we have hot X-ray gas. This purple emission shows the hot X-ray gas. And surprisingly or not, I think it's very interesting, the hot X-ray gas is not sitting in the in hydrostatic equilibrium in the gravitational potential of the galaxy. How do we know this? We know this because it has a very different morphology than the starlight. So the underlying starlight is shown here with the simple white DSS image. Okay? So M31 has a galactic scale outflow, and this galactic scale outflow is driven by the energy input by type 1a supernovae, and the mass is replenished by evolved stars. So that's the most interesting and most important message of this talk. Now, if you are interested in some details, then I urge you to listen to this. So, some introduction now. So, Marat gave yesterday a very nice introduction about the origin of X-ray emission in galaxies. So, here is a very brief list. AGM. I'm not going to talk about them. Because so many of you. Okay. Next. Okay. X-ray binaries. High-mass X-ray binaries and low-mass X-ray binaries. Of course, we are talking about all stellar populations, so it's going to be only low-mass X-ray binaries in the bulge of M31 and other nearby low-mass elliptical galaxies, since they are just no young stars. Then faint compact sources, cataclysmic variables, active binaries, and hot ionized gas. Finally, if you look at a galaxy in X-rays, you also see cosmic X-ray background sources, but we are not interested in those. And they don't belong to the galaxy itself. So, low-mass X-ray binaries, there's just a short summary what Marat told us. So, it's accreting black holes and neutron stars. Their luminosity is in the 10 to the 35, 10 to the 39 range. So, if you look at a differential luminosity function of X-ray sources, we are talking about this. So these kind of sources are fairly bright, and since M31 is so nearby, it's less than a megaparsec away. So with like relatively short or medium-sized X-ray observations, we can resolve actually all of them. So we can resolve with Chandra all of these X-ray binaries and very nicely remove. Then what we are left with is the active binaries and CVs, which are faint compact objects. Okay, so their luminosity, as you can see, we are now right here, is in the range of 10 to 27, 10 to 34 ergs per second. Whatever we do, we cannot resolve them in M31. We would need crazy deep proposals. Only the tip of this population can be resolved. And in other nearby elliptical galaxies, we just have no chance at all. Okay? So we have to deal with them somehow. But, good news. The distribution of these sources, of which we have a huge number, thousands and hundreds of thousands of sources in a galaxy population, follows the stellar light distribution as it has been shown for the galactic rich X-ray emission. Okay? And finally, let me go to the main focus of this talk, the hot ionized gas. So we know that we know it for quite a long time, so for many decades, that galaxies have hot X-ray gas. Okay? But the amount of hot X-ray gas is not always the same as you would expect. So, very naively saying, in a low mass galaxies we have very low amount of gas or no X-ray gas. A good example for this is M32, where no hot X-ray gas is detected at all. We still see unresolved X-ray emission, but it's not truly diffuse emission. So this is again the superposition of a large number of faint active binaries and cataclysmic variables. Okay? So this is what is shown on this image. Underlying image shows the X-ray emission. like a smooth X-ray emission, and this is the K-band distribution which follows the starlight. So they are all in agreement, which means, and also other considerations, for example spectral considerations, show that origin of the unresolved X-ray emission is faint compact objects in M32 and other very low mass galaxies.
Why can't I see individual low mass X-ray binaries there?
No, not low mass X-ray binaries. CVs, so cataclysmic variables and active binaries.
So you're saying there are no low mass X-ray binaries? Or they have been taken out?
They have been taken out here.
Okay.
So M32 is also very nearby.
Yeah, that's why I was surprised.
Yeah, sorry if I thought something silly. The other end of the range, M49 and GC4472, if you like phone numbers, this has a large amount of hot gas. So here the X-ray binaries haven't been taken out, but what you still see is that the diffuse glow, which really comes from truly diffuse emissions from hot gas, dominates the X-ray appearance of the galaxy. Okay, so I showed you the two extreme ends of the range, but what is happening in between? What is happening in medium size or as I call them, low mass elliptical galaxies? So a good example for this, and to study low mass elliptical galaxies, is M31. Why is it good? Why is it a good example and a good target? Because it's very nearby, so it's relatively cheap to observe, and we have all kinds of observations of M31. So here is some Chandra observations. It's a coordinate image of many individual X-ray observations, and what you see here. So this covers mostly the bulge region, and these are this. So all of these point sources are low mass X-ray binaries. Okay, maybe not all of them. There are a few cosmic X-ray background sources, but clearly most of them are low mass X-ray binaries. As I told you, we can remove them. What happens if we remove them? We are still left with something. We are still left with a diffuse glow. Okay. And you see, it's brighter here. It's not so bright in the outer regions here, so it has some peaked emission. So this is what I'm claiming, that it's partly originating from the hot gas, and in other part it originates from the superposition of faint compact objects. So what can we do? We can do a couple of simple tricks to find out where is the gas and where are the CVs and active binaries. So this is a surface brightness profile. So if you look at M41, it goes from roughly here, from the, northeast to the southwest of the galaxy, all the way. So we combine here XMM observations and Chandra observations as well. So red is XMM, blue is Chandra, and and the green shows the stellar light distribution as traced by Spitzer images, by quality Spitzer images. And what you can see here, that is all radii, all the way from here, except and here, it more or less follows the stellar light, except for the central part. What is happening in the central part? In the central regions of the galaxy, you have excess emission. You have a peak in the distribution. So what you see is that this is the position where the hot gas is. Okay. So let's extract some spectra. We can also do spectra. Spectra are good. So we can extract spectra in various regions because M31 is so well covered by XMM and Chandra observations. So let me extract actually 4 different spectra. We can do that. So we take a spectrum for the inner region where I showed you that there is a peak in the X-ray distribution, X-ray surface brightness distribution. Then we can take in the outer bulge region, so it still belongs more or less to the bulge, unless I put these little circles or ellipses to wrong places. And we can also extract a disk region, where there is not much star formation. And we can also take M42, about which we know that it doesn't have any hot gas. So we take the spectra of all of these regions, okay. We normalize them to the same starlight level, and then we look at the spectrum. This is how it looks. Whoa, funny, isn't it? There is one outlier, the central region where we had the peak in the surface brightness profiles. Everything else is more or less the same. Okay? Interesting. So, since it's so nice, I can just divide it into 2 and say that above roughly 1.5 kV, so I couldn't decide, so I just put there 1.2 kV. Everything is the same, and this part, as it was explained yesterday in my mark, can be fitted by a power law, and can be attributed to faint compact objects. But below 1.2 keV, the situation gets more funny. So in each of the spectra, we see a little bump, a little soft excess component. This is due to the contribution of active binaries, which have a soft spectrum. But in the central region, we have a big soft component, which is coming from the hot gas. Very nice. So overall, just to repeat, we have two X-ray emitting components. So the broadband component, which originates from a large number of faint compact X-ray sources. And of course, just as observed in other galaxies, this exhibits a very good agreement. So the distribution of this population exhibits a good agreement with the stellar light distribution. Okay? Whereas in the center, we have soft emission originating from hot gas. Is it surprising? Yes, it's interesting, but not very surprising, because we have been known for quite a while that the center of M31 has hot gas. For example, Jimmy Irwin and Joe has also pointed out, already using USCA and Rosat observations, that M31 in the center has hot gas. They even measured the temperature. They found the temperature of 0.38 keV, which is in perfect agreement with what we are going to find. But what is really interesting is the spatial distribution of the gas. So, the big annoyance when we study the distribution of the hot gas is that there is a big gradient here. So you see it drops an order of magnitude within a very small angular size. And what you want to do is you want to get rid of this annoying gradient, which is coming from the drop in the stellar light. So in order to make a nice X-ray image, what was in my very first slide and where I explained you everything, you have to do a very simple thing. So in order to get the gas distribution, you take an X-ray image, and then you subtract the near-infrared, in this case the Spitzer image, which near-infrared image you normalize with a normalization factor, which is obtained from this profile. Okay? It's a very simple trick. Actually I wrote it here. And this is what you get. Okay, I'm lying, this is not what you get. This is what you get if you also add the Spitzer 160 micron image, and if you add a DSS image, and if you do some Photoshop with the X-ray and you make it purple. Then this is what you get. Okay? Just proper science. Photoshop is important. No, not Photoshop, GIMP. So, let me be more serious. Numbers are serious. Okay? So, temperature of the gas, 0.3 keV, roughly. Luminosity, those who like numbers, 2 times 138 ergs per second. And also, the gas mass is just as Brand mentioned. I mean, he was quoting a number close to 10 to the 7, if I remember correctly. So, in the hot X-ray gas phase, we have 2 times 10 to the 6 solar masses of gas. Okay? And the cooling time is 250 megayears of the gas. So, right now, it's not very relevant, but it will become relevant in a second. So, you see that the gas, just as I explained in the first, it doesn't follow the stellar light, which is like in this direction, but it shows a distribution perpendicular to the major axis, and it suggests that it may be outflowing from the galaxy. So why you see this hole here, why you see nothing here, you may be asking from me. Why does it look so funny? It looks so funny because of the orientation of M31. So what you see here, this part is in front of us, this is in front of the disk, and this part, this and this part is behind the disk. Okay? So here you have absorptions. So the warm 0.3 keV gas gets absorbed here and also here, and since there is not a large amount of cold gas and dust here, no absorption here, so you can see it very nicely. You can see the hot X-ray gas very nicely. So what it all suggests is that this gas is oriented in a direction perpendicular to the disk of M31, and it may be outflowing because Okay, but how is this outflow working? So, how is this outflow working? Where does the gas come from? Where does the gas which is leaving the galaxy come from? It comes from stellar yields, from evolved stars, such as AGB stars, for example.
Is the lower side the near or the far side of the galaxy? Go big.
So
The lower side of the far side. The lower side is the far side.
like this.
Yeah, okay.
Yeah.
So I also have a basic question. Is that number has been corrected for absorption or not? From our galaxy and from the
Yeah. No, that's the half to 2 kV band which hasn't been corrected. If you correct it for absorption, then it's factor of 2 bigger. So, mass loss rate. So where does the gas come from? The gas comes from stellar yields, and the mass loss rate in the badge of M41 is roughly 0.06 solar mass per year. You know the stellar mass, so you know how much gas we have. 2 times 10 to the 6 solar masses. You just make a simple calculation, and you get that you can replenish this gas in 35 million years, okay? Which is much less than the cooling time. Okay, so can type 1a supernovae add enough energy, contribute enough energy to lift the gas from the potential? Well, the short answer is yes. So if you assume this energy, 10 to 51 joules per second, then the total energy is roughly this amount, 3 times 10 to the 40, and in order to lift and heat the gas, you need roughly 1/3 of this energy. How the coupling works exactly, don't ask me, I don't know. Okay, so I showed you that in M41 we have an outflow, which is perpendicular to the disk and is powered by type 1a supernovae, and the outflowing material is replenished by stellar yields. So, let me be ambitious here and ask whether there are other examples. Can we be ambitious enough to go beyond the megaparsec and find other galaxies where we also may see such outflows? Okay? Wow, we were so ambitious that we tried this. And the answer is yes, we can see. So, here is NGC 4278. It's an elliptical galaxy, it's now a really elliptical galaxy, which is a really X-ray cool galaxy. So it doesn't have much gas. This is M104, or if you like galaxy names, then it's Sombrero. It's an S0 galaxy, and it holds some X-ray gas, but it's still not a very X-ray gas rich system. So I don't want to bore you again with the same kind of details. You can do profiles, you can do spectra. It will be all the same, just like for M41. And again, if you just normalize everything to the same stellar light, you will see exactly the same spectra. It will just lie perfectly. So, if you remove again the EVA compact X-ray, compact faint compact objects, so CVs and active binaries, and you are left only then with the gas distribution, this is what you have. Again, it's like a bipolar outflow, a bipolar gas distribution, which suggests that the gas may be outflowing. A similar conclusion was achieved by Daniel Wang and Juan Li for Sombrero. And again, the conclusion is always that the outflowing gas mass can be replenished by evolved stars in these size, so in smaller size galaxies, and the SM1A type of supernovae can lift the gas from the potential. So now we have 3 examples, and you may become again very, very ambitious, and you may ask now, are we detecting these outflows routinely? The answer is no. No, we aren't. The issue is that the X-ray luminosity in these galaxies is very, very low, or relatively low. So it's 2 times 10 to the 38, which corresponds to not even too bright X-ray binary, low mass X-ray binary. Okay, and it's distributed over a whole big surface area. So overall, these are very demanding observations, and since the emission measure is proportional to the density square, so it's not very trivial to see these. But if you consider, and such outflows in low mass ellipticals should be very common. Since, for example, in 1 gigayear, evolved star, the stellar yields are roughly 10 to the 9 solar mass on average. So it's a huge amount of X-ray gas. In terms of X-ray gas, it's a huge amount. It's comparable to what the most massive ellipticals are having, like NGC 4472 or M49, which I showed you in the beginning of the talk. Okay? So it's a huge amount. And in these low mass elliptical galaxies, we definitely do not see that much hot X-ray gas. So even though we do not see them, they are leaving the galaxy. So why do we care? An important aspect which was already mentioned by Joe is that type 1a supernovae do not only add energy, but they also contribute with iron. So specifically, each type 1a supernova gives roughly 0.7 solar masses of iron. But if you consider the case of M31 and assume that the iron is perfectly mixing with the ambient medium, then what you would see to expect that the hot gas has a 6 times solar abundance, so it's a supersolar abundance. Okay? But we don't see this. Whatever we do, we see strictly subsolar abundances in M31. So, question, which I'm not even going to try to answer, what happens to the iron? One theory is that it doesn't mix effectively with the hot gas. And I think with this note, I finish my talk, and thank you very much for listening.
So, very nice. The question, so did you actually look into another galaxy, and given the star formation rate, do you have upper limits that are below the expectation that you got from those 3 examples? So is that counterexample given the observational sensitivity?
As in, so what? I didn't understand.
Basically, you expect for a given star formation rate an outflow rate, right?
No, I mean, there is no star formation. These are type 1a supernovae, so these are type 1as which are only associated with the all-stellar population.
Okay, yeah, it's different. So if there's basically, assuming this all-stellar population gets typically supernova rate that powers the outflow.
Okay.
So
now I understand what you mean.
Basically, is there an upper limit that is below this expected sort of type?
Yeah, so in bigger galaxies which have a deeper potential, type 1a supernovae do not give enough energy. And this is why in big massive galaxies...
No, but for these type of galaxies?
These type of galaxies, no. I think, once you do not drive the gas out of the galaxy, it just accumulates and accumulates, right? And then
saying that, suppose you take a 1/10 big elliptical galaxy at a 10th L star. Do they all look the same? Or do you see X-ray emission in some and not much in others? So he's asking if the wind scenario is consistent from galaxy to galaxy.
Well, there is a big variation. So if you take like a galaxy at a given stellar mass, there will be big variation in the X-ray properties of the galaxy. So some will be gas poor, some will be more gas rich, right? And the exact reason of this is unknown. Mike Anderson talked about that it may be the dark matter halos which regulate everything. So the answer is that no, it's not everything is so not all low mass ellipticals or not all galaxies are exactly the same. What also matters is the environment. So if you have a group environment, a cluster environment, then you are less likely to see outflows.
So you use this technique of basically scaling the near-infrared light with some value to basically predict the contribution from X-ray emission from some stars. And it seems to work really nicely. You've done it in different galaxies, you've done it in a galaxy function of radius. What constraints, if any, does it put on variations of the IMF?
Good question. I would have to think about that.
Somebody has done that
and
claimed that it rules out the bottom heavy IMF. I can look up the reference.
It's the group of people at Michigan State whose names are not documented.
So when you have a wind, you get a radial distribution that's somewhat different than down gas and hydrostatic equilibrium. And this is something people try to see with Rosat, where it's just too faint a feature. Do you see that it kind of turns over faster than if you have bound gas? Do you see that? Or is the non-axisymmetric flow make it difficult to detect?
Yeah, no, I would say that no. So it's hard to detect that. And so strongest argument that it's in an outflow state is the morphology of the gas and the orientation of the gas.
One more question?
I was curious why there's a bipolar outflow in an elliptical. What is coordinating the outflow? So you showed one of them there was this bipolar morphology. I wonder why you get that.
That's a very good question. Why is it bipolar and why is it not like
Why not isotropic?
why not like a or a nice subsonic outflow? Maybe something with the energetics. Maybe that.
It's not a vacuum.
Yeah,
It's-
well, can
it's-
Tim, maybe Tim can comment.
I mean, some 70% of your elliptical galaxies are actually fast rotators with embedded stellar disks, so there is some third axis in most of them.
So that's why it's perpendicular to
What's
this.
that one?
Do you have, I mean, do you guys have imaging of that? Is that in you?
If you give me the number, I'll.
What was it, 4672?
40 to 78.
4278. 4278. I'll check, come back.
So it does have a full disk,
It
okay.
does have a disk, and it's a well-known liner or
Right, and it has a,
soft seaford or something like that.
and then the cool disk is also seen in the X-rays, so. And this may be a compact core array.
Yeah, yeah.
Let's thank the speaker.